Good afternoon, everyone. My name is Cottuli. I'm the Vice President of Product and Service at a company called Wright. Thank you for coming to the session today. We're going to talk about containment readiness and trying to bring you through some of the major decisions around containment and some of the benefits that containment can bring to a data center, airflow management strategy. And with that, as far as the agenda goes, I think we'll just talk a little bit about who we are as a company and why should a data center even consider a containment strategy. We'll cover some of that, some of the real benefits. A lot of people would like to talk about containment is good, but really, how do you get to those tangible benefits? And then the different types of containment. One of the big questions around containment, we'll make some attempts to answer some of those big questions around which one is better. If you have the clean sheet of paper, it's kind of tough to make all the different decisions. And then which one is best for my data center? How do I make some of those trade-off type decisions around selecting a containment strategy, and really how do you get started with all of that? We're hoping to get through this in about 30 to 45 minutes and keep you on time for the schedule. With that, who are we? We're Wright. We're essentially a global leader that outfits technology-intensive environments. Whenever there is an intense amount of technology and you've got the complex problems of delivering power and cooling to that type of environment, that's where you're going to find Wright. And really what we do in that environment is we bring innovative product development and product solutions with quality manufacturing to solve real customer problems. Our sales model is focused on identifying those customer requirements, constraints, and turning those into really future-proofing solutions that help our customers not only today, but in 2-3 years down the road. Ideally, we serve both commercial and government markets, and we can talk specifically about some of those clients, but we keep very focused on those markets. And we're 75 years old. The company's been around for a long time. We've grown up in the data center industry, and one of the little known facts that I like to tell everybody about Wright, but believe it or not, Wright is one of the first companies in the data center industry that took on storage in the data center. Does anybody remember what storage was when the data center was first invented? Storage was actually on paper. They were on paper cards. And Wright made the paper filing systems for storing the punch cards that computers ran on for their memory. It was actually our first foray into the data center, and from there we've been innovating ever since. And of note, Wright was recently acquired by Eaton. We are now part of the Eaton family. Very proud to be part of the Eaton family, and what that does for us is help us bring even more holistic solutions to our customers and our clients. So that gives you a little bit idea of who we are. One of the things I wanted to talk about in the legacy data center and why containment is being even put on the table is something we call chaos cooling. A lot of times legacy cooling designs are used for many different purposes besides actually cooling the IT load. Meaning the air streams are used as cool air plumes to provide just this cool air mass in front of the IT equipment in hopes that the IT equipment are going to draw air from that cool air mass. And it has other purposes as well. A lot of times you'll see cool air in a data center or static pressure in the underfloor plenum being used to move stagnant warm air towards a return. Again, all of these are problems that are solved anecdotally inside a data center. No real direct tangible results, and really results in what we call a chaos methodology for the data center. And one of the big problems that we see with that methodology is it's unpredictable. It's generally, when you make small changes in that environment, you have no idea of what the end effect's going to be. So that is a problem in a data center. No one likes unpredictability in a data center, and we're going to try to present some ways to remove that component of unpredictability. So why should you consider containment? Well, a lot of things that we like to think about when we talk about containment is what we call a supply path delta T and a return path delta T. Simply looking at the drawing gives you a real good idea of what the supply path delta T is. You've got air coming out of your HVAC equipment, and represented here is just a perimeter type crack unit, and air that's brought into your IT equipment. If I was going to take the average inlet of all the IT equipment and the average outlet of all the supply air, there'd be a delta T there in a legacy data center. The wider that delta T is, the more chaos cooling exists in your data center. Conversely, turn that around. In the return path, if I go right to the outlet of the server equipment or any of the IT equipment in a data center, and I meter that temperature coming out, it's actually quite warm. It would not be unrealistic to see in the 90s in that exit temperature of a piece of IT equipment. However, when I go look at the return temperature of the HVAC equipment, it's no way near 90 degrees. Historically, I see that somewhere in the high 70s, if I'm lucky, in a legacy type data center. So ideally, what we're trying to do is identify the supply path delta T, the return path delta T, and drive solutions in each one of them. As I drive solutions in the supply path delta T, that improves the cooling system's capability to cool the IT load. There are ways to overdo it in there that you can create waste as well, and that actually happens in legacy data centers where all they do is supply a massive oversupply of air. Why are they doing that? Well, they're managing the supply path delta T to try to compress that and cool the IT equipment. However, on the pain of that type of methodologies on the return side is a really huge delta T, meaning the IT equipment's still putting out 90 and you're getting 72 back to your HVAC system. So a balance between managing supply path delta T and return path delta T is really what containment is about. Ideally, how does this manifest itself in the current data center today? If you've been in data centers, particularly legacy cooled data centers, you've seen these three typical problems. The first that we're talking about is recirculation. A lot of times warm air is making it back to the front of the IT equipment and is being pulled in as a supply air temperature. And obviously as that continues to feed on itself, it will eventually get too hot for the server equipment, and this creates hot spots. And what does that cause you to do as a data center owner? Well, you'd normally either bring in additional cool air, now start to use air to blow away the warm air, or you're going to oversupply and create this cool air plume, or you're going to abandon the IT space. You'll make a general judgment that says, all right, the top 5 view of all my racks, because of a stratification problem and the warm air is coming down, are relatively unusable. That's not effective management of the data center either. Additionally, one of the other things is bypass air. And what bypass air is what is normally happening when you're doing that oversupply methodology. Air is just going straight out of your HVAC equipment and back into the return of the HVAC equipment. And that doesn't necessarily have to be the same piece of HVAC equipment. It could be system 1 and system 2, which we see that a lot as well. Either way, the cool air provide no useful work for the data center owner. It actually short-cycled and went back to the HVAC system. So that's how pretty much chaos cooling manifests itself in today's data center. And we're going to try to avoid as much of that as possible. Why? Well, we want to be efficient, right? Pretty much being efficient is matching supply and demand and providing that supply as efficiently as possible. Ideally, we want to keep the operating costs for a data center as low as possible. We want to look for ways to trim this throughout the data center. Cooling is just one piece of the pie that is an opportunity to provide that efficient operation. Well, why do you want to be efficient? Well, besides saving the real dollars, you can easily see some incentive plans that are on the way into this type of industry based on either EPA or carbon type credits. All of that is coming to the data center, and being efficient in bench modeling that efficient data center is something that the data center owner is going to have to deal with. It's easy to go ahead and adopt containment and capture what is on the table for an efficiency entitlement. What I was what I wanted just to be able to show you is here's two traditional data centers, one in a legacy format and one in a contained format. This happens to be total containment with less than 3% leakage front to back of the contained aisles. What that means is no more than 3% air needed to supply any type of overage, any type of leakage in the containment area. This happens to be a chimney-based containment, but it is true for pretty much any type of containment, and I'll get into that in a minute. So really what you're seeing here is 8 crack units to be able to get this traditional data center up and operational, and all racks are reporting acceptable inlet temperatures within the ASHRAE range. And this is just one part of a CFD. We can get in a lot deeper, but as you look on the chimney type side, you can see 3 cracks have actually been taken offline. Now you can look at this either way. You can be cycling cracks that you already have. You can not buy the 3 cracks and save you the operational cost as well as the purchasing cost of these cracks. But as you look at this, the heat containment data center, you can see a lot more of the racks actually have a lower inlet temperature currently displaying through the CFD model. And as I really start to peel the onion and look at the actual attributes and the values, the legacy design versus the heat containment or the chimney type design, there's some important points, and really the number one thing that we want to look at is these numbers here. This is the airflow supply and the demand. So as you look in the legacy unit, 132,000 CFM of supply, and I'm getting 85,000 CFM of demand, meaning the IT equipment is saying, give me 85,000 CFM and keep it within ASHRAE limits. You can see the maximum inlet temperature is actually one rack reporting over ASHRAE at 86 degrees Fahrenheit, but you're giving it 132,000 CFM. That's not necessarily matching supply and demand, but in a legacy system that is acceptable. And having 1 or 2 rack spaces that have some high temperatures that are either going to be abandoned as rack space or a hot spot that will be not populated is acceptable in a legacy design. Take that over to the heat containment design, and you're down below ASHRAE at 80. And actually, if you look at it, the supply and demand is inversed. Right? We're actually starving the IT equipment. The IT equipment is saying, give me 85,000 CFM, yet I'm only actually giving you 82.5. So I'm starving the IT equipment, granted by less than really a percent or so, but the point being that you can actually match supply and demand, maintain a stable environment, keep the inlet temperatures in a predictable range, and still get the performance out of the system. So ideally, that's the capture, that's the efficiency that is available for anyone that's looking at a containment strategy to adopt, is capture that type of waste, that the difference between that 85,000 demand and that legacy oversupply of 135,000 CFM. And that fan energy to move that air is really what you're saving. How does that work out? This is just a typical example of some of the efficiency and the different pieces of the pie that consume energy in a data center. And this is why we see the cooling infrastructure as a particular component that is available to go capture and drive some efficiency savings. As you can see, the difference between the two, facility 1 and facility 2, with the same amount of energy being consumed, a lot more of it is making it to the IT equipment because of an optimized facility. As I drill in and look at just the fan energy consumed between the two different facilities, I'm saving about $60,000. So that difference of 85 to 135, it ends up being about $60,000 a year for this size data center. Obviously, this is a relatively small one, and it does scale up with the size of your data center. So there's a significant amount of money potentially on the table.